Okay, so today we're actually going to be doing a lot of review of material from grade 10 and 11. And so it kind of lends itself well to the fact that we're not going to spend like a ton of time doing things today, just because it will be pretty quick. A lot of it should be familiar to you guys. If it's not already familiar, then I would recommend going in and you notice here that I assigned a ton of homework problems. Especially for page 443, those are all like one-line questions, okay? So those are sort of rapid fire, just get your feet wet with things again. Mostly those questions are stuff that you would have done in grade 11. And then the questions on page 458, that's more of a review of grade 10 optics, okay? Okay, so let's just kind of summarize a bit about what we know about waves and light. Hey Tycho, is the YouTube stream better for you today? Or are you having any trouble with the connection, or is it pretty okay? Okay, that's good. Excellent. Okay, sounds like a plan. Okay, so let's get started. So I'll kind of blaze through a lot of this, just sort of reading it. Interrupt me if anything seems kind of unfamiliar, but it should all seem familiar, especially if you've taken advanced functions, right? Because a lot of this boils over with advanced functions, a lot of the terminology involved, okay? So a periodic wave is a wave that just repeats with time or distance, okay? So something like a water wave is an example of a periodic wave because it just repeats with time, or the wave that you might see from alternating current is a periodic wave, okay? Some more terminology here. A wavefront is the continuous line or surface at the start of a wave as it travels with time, okay? So the way that I would visualize that is if you've ever been in one of those wave pools, when it starts, when the big bar at the front starts oscillating up and down, the initial wave of water, that would be the wavefront of the wave, okay? So it's the start of a wave as it begins to travel, all right? This diagram is kind of our main diagram here, okay? So there's a few quantities listed here. There's a few that aren't listed. So the wavelength is the distance between, say, a crest, and I'll indicate those in a second, or a trough and a trough. Basically, it's just one unit of, or one cycle of our wave, okay? So the way that I usually think about it, here they have the wavelength indicated between where the wave passes through its equilibrium position. You could also measure the wavelength from the crest of the wave to the other crest of a wave, right? So this distance here would also be the wavelength, okay? Also the wavelength. The symbol that we use for wavelength is this Greek letter lambda, okay? We could also measure the wavelength from the troughs of the wave, okay? So trough. This would also be the wavelength, okay? So again, it's just essentially one unit of the wave, okay? It's one unit, and then that unit just repeats with time, all right? One term which may be familiar to some of you, interrupt me if it's not, is the phase of a wave. And the phase, or phase shift, is the offset of a wave from its reference point, okay? So actually, in advanced functions, you had a nice way of describing this, right? We describe the phase shift. The phase shift is just a horizontal translation, left or right, of our sinusoidal function, okay? So the phase shift just indicates, for instance, if a wave, say, starts at a crest versus if a wave starts at a trough, those two waves would be out of phase with each other, okay? Because they start at different points within the cycle. Everything else about them could be identical, except the starting point that they start at, okay? So definitely rely upon your advanced functions knowledge here. This is just a horizontal translation of the sinusoidal function, okay? Is this all pretty familiar to everyone? All of these wave properties? Okay, cool. Yeah, peak. Yep. Trough is the low point, the minimum. Yeah. Okay, so our first equation, this is something that you should have seen for sure in grade 11 waves. The universal wave equation allows us to relate the speed at which a wave is traveling to either its frequency or period and the wavelength. Okay, so there's two equivalent formulas here. Either the speed of the wave is equal to the frequency times the wavelength, or an equivalent formula, the wavelength divided by the period. And here we've used that the relationship between frequency and period. Frequency is just 1 divided by the period. Okay, so that's another relation that we see. All right. Okay, so we'll practice the wave equation in a second here. Just a few more quick little definitions here. So going all the way back to the physics unit of grade 10 science, you most likely learned about two things, or focused on two main things. Reflection, so you probably drew a whole bunch of ray diagrams on mirrors, and refraction. So those are the two big things that we learned about. We're going to summarize those two things today. So the main thing to understand both reflection and refraction, we use what's called the Ray Approximation. Okay, so the Ray Approximation states that light propagates as though they are moving in straight lines called rays. Okay, so let's say I have like a flashlight and I turn the flashlight on. Essentially there's a beam of light that travels in a straight line, just a single narrow straight line until it hits something. Okay, that is the Ray approximation of light propagation. Okay, so back in grade 10 when you were learning all these optics concepts, you probably drew a whole bunch of diagrams like, oh, if a ray passes through the focal point of a mirror and it reflects like this, or if a ray passes between the boundary of two media, it'll refract in a certain way. They're pretty fun. I actually hated them. I hated them when I went through it the first time, but then when I saw it again, like when I was tutoring and teaching, I found a new appreciation for it, I would say. It's quite fun, and the rules aren't so bad. And actually, we're going to kind of go through a couple of the rules today. We're not going to be drawing any ray diagrams here, nothing like that. We just have to know sort of the theory behind that concept. Okay, it'll become important in a bit. All right. So reflection occurs when there's some change in direction of a light ray when it meets an obstacle. Okay, and specifically, this is when the incoming ray and the outgoing ray are on the same side of the obstacle. Okay, so reflection, I think we're all familiar with reflection, right? You stand in front of your mirror, the light that's shining on you gets reflected off you into the mirror, and then the light bouncing off the mirror gets reflected into your eyes and you can see yourself, right? So here's a diagram for reflection. So here we have our incident ray. It contacts the mirror and becomes reflected. So the outgoing ray is called the reflected ray. The angle of incidence is the angle that's measured between the incident ray and this normal line here, right? So this normal line is just a line that's oriented 90 degrees to the mirror. Okay. Okay, and we have a special, or we have a rule describing the angle of incidence and the angle of reflection. So when this occurs on a flat surface, the angle of incidence is equal to the angle of reflection. Okay, so the angle that the light is incoming at is the same angle as the light is outgoing at. So these two angles here are actually equal to each other. The angle of incidence and the angle of reflection, these are equal to each other. Okay. And that rule is just stated mathematically down here. Theta I, so the angle of incidence is equal to the angle of reflection. Okay. Okay, and that's pretty much it. The only other couple like very small definitions here, but when the reflected light rays all propagate in the same direction, we call it a specular reflection. But then when the light rays are scattered in different directions, so like off an uneven surface, we call it diffuse reflection. Okay, so just a couple little definitions there. All right, so say if you look at a mirror is an example of specular reflection because the light rays are the reflected light rays are all coming in the exact same direction back at you. Okay, but say if you took a piece of right, but we're talking strictly about reflection though. So here's an example. You take a piece of tinfoil and you scrunch it up, and so the surface is very uneven, and then you hold it up. You're not going to see any reflection in there because all of the light rays that are hitting the piece of crumpled up tinfoil, they just diverge off in various different directions. Okay. I have a couple quick examples here just of the universal wave equation. So first example here, sound waves travel in water at a speed of approximately 1.5 times 10 to the 3 meters per second. Oh, I forgot to take attendance. Give me a second here. Sorry. Okay, sorry. Okay, yeah, so the speed of the sound waves in water travel at 1.5 times 10 to the 3 meters per second. We know that the frequency is 4.4 times 10 to the 2 hertz. And all we're looking for is the wavelength. Okay, so we're interested in what the wavelength is, all right? So our universal wave equation states that the speed is equal to the frequency times the wavelength. And I'm just going to rearrange this formula. All right. Wavelength equals the speed over the frequency, which is equal to 1.5 times 10 to the 3 over 4.4 times 10 to the 2. Okay. I get a value of 3.4, roughly. 3.4 meters. And that's that. So the universal wave equation is very straightforward, right? Just a simple relation between frequency or period and the speed and wavelength. So really straightforward calculations. Okay. One more quick example here. Actually, this one's a little bit more important, but equally as easy. So here we're looking for the frequency of red light, and red light has a wavelength of 750 nanometers. Okay, which is equal to 750 times 10 to the negative 9 meters. All right. Now we're looking specifically here. The important part here is we're looking at red light waves. Okay, so red light waves travel at the speed of light, right? So the speed of light is a constant value. If you have actually, is it on this calculator? I'll check it out in a second. I think it is constant 28. Yeah. So Jenna, this on our calculator, it's constant 28. If you want the speed of light, the speed of light is 2.99. 79 times 10 to the power of 8 meters per second. Okay, or I mean, usually in textbooks and whatnot, they'll just use 3.0 times 10 to the 8 meters per second. Okay, and this light can reach that speed. You and I cannot reach that speed though. This is the speed of light. And we use the letter C to denote it, but really this is just the same as any other speed of a wave, right? So this is our V in the universal wave equation. Okay. So we do this exact same way as the previous problem, right? So we have our speed is equal to our frequency times our wavelength. But now we're looking for frequency. So frequency is the speed divided by the wavelength, which is just c divided by 750 times 10 to the negative 9. And I get a value of very high frequency, 3.99723 times 10 to the 14. Okay. And the units there are hertz. Okay. Any questions about that one? Or still pretty straightforward? Still pretty okay? Okay. Yeah. Okay, so now that we've done reflection, let's get into some refraction. Okay, so again, this should all be familiar from grade. Actually, there's one new thing here. We'll get to that, but this should be pretty familiar from stuff from grade 10. So first off, refraction is the bending of light as it travels from one medium to another. So let's see if this will work. I'm sure you've all seen this or something like this before, right? If I put my pen behind my water bottle here, right, I can see that. Actually, it's extremely hard to see here. One second. Let me. Let's see if I can't put my pen like this. Okay, so see in my water bottle right now how it looks like my pen is kind of bent, like it's not a straight line. Do you guys all kind of see that? That's because light travels at a different speed depending on what medium you're looking in. Okay, let's actually see if I can find a good example of refraction. Yeah, exactly. Like you would aim at a spot where the fish is not actually there, right? Yeah, so here's a better sort of same thing that I was showing with my water bottle, just a little bit cleaner here. So you can see that when the pen is put in the glass of water, you essentially it doesn't line up properly anymore, right? That's because again, it looks like it's bent. Obviously, the pencil is not actually bent because when you take it out of the water, it's perfectly fine again. What's happening here is the speed of the reflected light rays off the pencil are traveling at different speeds in the air and in the water, okay? And it's that effect, that refraction, that makes it appear as though it's bent, okay? And so refraction is all about describing this kind of phenomenon, all right? So let's get back to this. So one main thing that we kind of talk about oftentimes is we talk about optical density of a material, okay? So it's a property of the material that determines how light behaves when it travels through it, okay? So oftentimes when I'm going through these problems, I'll refer to, say, like more dense and less dense materials. Basically, a material that's more dense, light will travel more slowly through it, okay? So a less optically dense material, light will travel more quickly through it, okay? The index of refraction, again, this should all be familiar from grade 10, is defined as the ratio of the speed of light in a vacuum. So that's, again, C, which is the quantity that we defined earlier, 3.0 times 10 to the 8 meters per second. So it's the ratio of the speed of light in the vacuum, or in a vacuum, relative to the speed of light in another medium, okay? So because the speed of light in another medium can never travel faster than the speed of light in a vacuum, this ratio will always be larger than 1. Okay, so C will always be greater than V in this equation here, which means when you look at the values for the index of refraction, these are just, you can look them up online or in a table. There's a table in section 9.2 of the textbook, and the values are all bigger than 1. That's because this ratio is always bigger than 1. Okay? Now, I think here's the first new thing. To determine how light will refract, so here's a diagram of light rays refracting, right? We have a incoming ray from point P, and you learn... Okay, so to define what's going on here, so N1 is just the index of refraction from our incoming medium. N2 is the index of refraction for our outgoing medium. And then theta 1 and theta 2 are just our, theta 1 is the angle of incidence. And theta 2 is our index of refraction. Oops. Okay. And I think, Aiden, you were kind of mentioning this. If you play around with all of these formulas, and again, I think the textbook kind of derives this. It might. I know it derives Snell's law. It has a really good derivation for Snell's law. If you'd like to kind of get more intuition behind where this formula even comes from, feel free to ask about it. I don't mind making like a separate video on it. It's a pretty good explanation in your textbook. But for now, we're just kind of taking it as a fact, okay? If you kind of play around with all these formulas, so the n equals c over v and the universal wave equation, you actually get another formula. N2 over N1 equals the wavelength in the first medium divided by the wavelength in the second medium, okay? And so these two formulas are pretty much, they're giving us, or they're using different pieces of information, but they're the same idea, right? They're kind of the same concept. Okay. Okay. Let's do an example. So, example: calculate the angle of refraction. So we're looking for the angle of refraction, meaning we are looking for theta r for light moving from a vacuum into a plate of glass. So the plate of glass has an index of refraction of 1.47. The angle of incidence is 40 degrees. Okay. So I'm a fan of just drawing a picture out for this. So let's call this part A. I'm always a fan of just drawing a picture about what's going on here. Okay, so we have our interface between vacuum on top and the glass on the bottom. Okay. So the index of refraction for vacuum is just n equals 1, right? Because light moves at light speed. V is equal to c in a vacuum. So we call that N1. N2 down here is 1.47. The angle of incidence, and again, the angle of incidence is measured with respect to the normal line here, right? So there's our normal. Here's our incoming ray, our angle of incidence right here, theta 1. Theta 1 equals 40 degrees. Okay. What we're looking for, what we're interested in now, is what the angle of refraction will be, right? We want to figure out what theta 2 is, okay? Or theta r. I think I called it theta r up top. I'll switch that. Theta 2. Okay. So for this, we are just going to apply Snell's law, right? N1 sine theta 1 equals N2 sine theta 2. All right, I'm going to rearrange this for theta 2. So I get N1 sine theta 1 over N2, and then the whole thing is inverse sine. So theta 2 is sine 40 degrees divided by 1.47. I get a value of 25.929 degrees, so approximately 26 degrees. Okay. Okay, part B. The light continues through the glass and then emerges back into the vacuum. calculate the angle of refraction when the light exits the glass. Okay, so what's going to happen? So this is part A. So for part B here, we're going to have a similar setup, except that the light is traveling back from the glass back into the vacuum. Okay, so it is, again, let's draw our normal line out. Our angle of incidence now is actually the value that we found from part A, right? So that's our new angle of incidence. Okay, our theta 2 is our new theta 1. So theta 1 is equal to what we found in part A, so 25.929 degrees. Okay. Should it be the same value? Yes, but let's see why it ends up being the same value. Or it'll be the same value as our original angle of incidence. Yes. Yes. So this outgoing light ray is going to do something like that. We want to figure out what the new angle of refraction is. Okay, so we want to figure out what theta 2 is in this case. Okay, so same idea, same setup. N1 sine theta 1 equals N2 sine theta 2. But now I'm rearranging for theta 2 here, so same idea. Theta 2 equals sine inverse N1 sine theta 1 over N2. But now my N1 and my N2s are switched here, right? So in this case, N1 and N2, so N1 is the index of refraction of glass, so that's 1.47. N2, that's 1. And then theta 1 is my 25.929. Okay, and when I do this, just like you said, Casa, I'm actually going to get a value of 40.0 degrees. Okay, so I get the exact same index of refraction as I did from my initial angle of incidence, right? When the light ray was initially passing into the glass. Okay. So that's part B there. Let's go through part C. Suppose the light